Good morning, everyone. Welcome back. Thanks for your determination, for sticking with us. Thanks for your patience. We very much appreciate it. Our first speaker today is Steve Hodges. We're going to jump right in. Steve is going to be talking to us about addressing accessibility with physical computing. Steve, the mic's yours.
Thanks, Roy. Hello, everyone. I'm super excited to be here today and have this opportunity to present some ideas to you. So, as Roy said, I'm Steve Hodges. I work for Microsoft Research. I'm in Cambridge in the UK. So it's the evening here for me. I know we've got people from all around the world, and I'm actually going to start with an apology. So the title of my talk changed actually overnight, based on some of the great discussions we had yesterday, and obviously not just the title, but the content of my talk changed quite a bit. So the slides are coming in hot, and in particular, I've done my best in terms of tagging the images and so on and so forth with the copy of the deck that you have access to. But please accept my apologies for that not being quite as polished as I would have liked. So by way of introduction, I was going to start actually with a disclaimer. So I am a hardware researcher. I'm not a computer science education expert, and I'm not an accessibility expert. So please bear that in mind. And in case I kind of allude to any expertise in those areas, your job is to help keep me honest. But as a hardware researcher, my day job really is to imagine, design, build, and evaluate different types of interactive device. So this slide here shows examples of things I've worked on: new types of input device, environmental sensors, new types of display, for example. But you might notice that some of the things in this slide aren't really devices. And I also work on tools and systems that help other people create electronic devices. And I'm going to spend quite a bit of time today talking about one example of this, and that's a system called .NET Gadgeteer. So .NET Gadgeteer is a physical computing toolkit, if you will. For those of you not familiar with the term physical computing, I put a definition here on the slide, combining software and hardware to build interactive, physical systems that sense and respond to the real world. So physical computing, of course, is therefore used to describe many of those interactive devices I put in the previous slide. And often these interactive physical systems support communications. So that means that devices can talk with other devices, and so broadly physical computing also relates to the IoT. So .NET Gadgeteer was designed to enable the quick construction, programming and evaluation of physical computing devices. We actually created .NET Gadgeteer in the first instance as a tool to accelerate our own device research. We wanted to be able to build stuff more quickly, so we could try more things out more quickly. Gadgeteer consists of a set of hardware modules. Each of them has some kind of functionality. So in the picture here, some example modules. So there's a joystick here. There's a light sensor here. There's some LEDs here. And these modules all plug into a processor board, and the processor board is programmed so that it consumes some of these sensor inputs and maybe controls the output like the display. So when we created Gadgeteer, we aimed to do two things which are often difficult to do simultaneously. We wanted a very low threshold so that simple gadgets could be made really quickly, a matter of minutes. And we also wanted a high ceiling so that you could build quite sophisticated devices with it to support our research. Sophisticated both in terms of the hardware they supported and in terms of the software functionality. So we kind of thought of Gadgeteer in terms of pillars, and so the first two pillars relate to hardware and software, as I just described, but we were also conscious of this third pillar on the right, the notion of design and the form factor of devices. We wanted a system that you could use to make quite compact devices and was compatible with technologies like 3D printing, which back then were still emerging. And to give you an example, here's an example of something we built, an alarm clock. In the middle at the top there, you can see the modules it's made from. There's a main processor board in the middle, and there's two little OLED displays on either side and various other sensors and controls around the outside. At the top right, you can see how these modules all fit together, and down in the bottom right, everything is a photo of everything actually inside a 3D printed enclosure. So that's physical computing. What has that got to do with accessibility and computer science education? Well, as we were developing .NET Gadgeteer, we started showing people. We demoed our devices to people, and it was a bit frustrating actually, because we were trying to show people these amazing devices we built, and time and again they were more interested in the platform we'd used to build the devices rather than the things themselves. And some of the people that saw our devices and our platform were teachers. And to put this in context, this was before the big K-12 computer science education revolution that was kickstarted by things like the Royal Society report and Obama administration Computer Science for All initiative. So this stuff hadn't happened at that time. Around the world, mostly, for the most part, K-12 students did not have computer science in their curriculum. They were not really learning about programming or computational thinking. Of course, we taught all our students, we taught them ICT. We were teaching them how to use existing computer systems. We just were not teaching them how to create the computing systems of the future. So one of the many people who were beginning to wake up to this concern and who also saw .NET Gadgeteer, saw our prototypes, was a lady called Sue Sentence. And we teamed up with Sue and ran a number of pilot studies in the UK and the US with .NET Gadgeteer in high schools. So in the UK, I think we had 16 schools, and we worked with the 11 to 17 age group, and we had a slightly older cohort of children in suburban public schools in the US, in 3 suburban public high schools. And I won't go into the details of the work. There are some publications which go into a lot more detail about exactly what we did and what we found. But in a nutshell, we uncovered many benefits to physical computing. So just to kind of sketch over these here, of course, there are technical skills that we were able to give the students. We were teaching them programming. We were teaching them high-level computer science concepts. We were teaching them about graphics and user interface and user interaction. And we also gave them a more holistic view from a technical perspective. So I think a lot of them ahead of time thought computing was all about programming, but through physical computing, we showed them there was much more to it than that. There are these other elements, and there, it's really a multidisciplinary field when you consider it more broadly. But we also noticed a large number of soft skills being developed. So first of all was creativity. The students naturally related to the technology and the task, and it just gave them so many ideas. And the ideas weren't, again, just about programming. They were all aspects of computer systems. So it created a very collaborative, inclusive environment, especially when students were working in groups. We would find everyone was included, and everyone, although everyone was exposed to the whole process, people found different areas. They found their niche, and they found the thing that they could contribute. Physical computing promotes a different way of thinking about solving problems, because a couple of reasons, I think. First of all, there are many different ways to solve a given problem, and so that gives you a different perspective. It's not like you have to learn the one way to do it correctly. And also, its very nature, you get very physical very quickly, and so it becomes a very iterative process. And again, that's a different way of problem solving. And of course, the tangible, tactile nature of the physical devices, the students find it very engaging, and it helps them make connections. And also, we found that there was a lot of opportunity for connections across the curriculum. So you might use your physical computing skills to build a device, but then you might deploy the device in the environment and use it to measure something, and use those measurements to inform what you're learning in biology or what you're learning in geography. And I think the final point I put there, which in some ways I think is the most important, was motivation. Our students, bear in mind in the UK, this was not part of the curriculum. You couldn't choose to do computer science and then get a meaningful qualification out of it at the time. So this was an extracurricular activity. The kids were doing this because they wanted to after school. And we found we had tremendous engagement. In particular, we got a very good balance, gender balance. We had as many girls wanting to do this as boys. And I think in part it was because the students were focused on the end artifact, right? So they had a goal in mind, and kind of almost by subterfuge, we taught them computer science along the way. But they certainly didn't see it as being taught computer science. They saw it as learning to build the thing they wanted to build. So I've got some photos here of things that students made, just to give you an idea. Up in the top left here is an alarm system. So we had this student, Jo, and she had this idea to build an alarm for an important piece of artwork, maybe like a vase. And so the idea is you would place the vase on top of this plinth, and there's a little push button there. And so that would sort of activate, arm the alarm, because the button would get depressed. And then if anyone took the vase, the button would ping open, and that would trigger the system. Lights would flash, an alarm would sound, and there's a camera. This black circle here is actually a camera lens. It would take a photo of the culprit. This is a Space Invaders game with a little joystick that moves the spacecraft around, and there's a fire button you can use to shoot missiles. Up here is an Etch-a-Sketch, the classic Etch-a-Sketch kind of game, with two rotary knobs to control the line that you draw on the screen. This in the bottom left is it's a reaction game. So coloured lights would light up suddenly at the bottom, and you had to press the corresponding button very quickly in order to score points. And in the bottom right, we've got a camera. So you can see that there's quite a lot of creativity here. People are building very different things. There's quite a level of sophistication in these devices, right? They're not just blinking an LED. And we even achieved, I think, our third aim with Gadgeteer, which was to have people thinking about the form of devices. And we've got some sort of more craft-like devices on the left, and on the right we've got some more sophisticated devices. This has been laser cut, the enclosure for the camera, and this enclosure was actually vacuum formed. So hopefully now you can see how physical computing can make computer science education more accessible, and computer science more broadly. But can we make physical computing itself more accessible? Well, there's already a big range of options in terms of physical computing. This table here is taken from a paper which was published at the beginning of the year. I put the citation earlier in an earlier slide. And the photos on the right give you some idea of the products in this space. In the left, we've actually categorized these products very broadly. And these groups, starting at the top, we've got electronic kits, and then we have, more or less self-contained programmable devices, or sometimes these are kits, modular kits, I guess. And then underneath that, we've got different types of board level solutions. So as we move down through these different categories, there is increasing flexibility. So very broadly, the products at the top tend to be more constrained in the range of things you can do. So in the case of a turtle, of course, you can map out any path you want, but fundamentally you're limited to mapping out paths. And as you move down the list, you find that you get more flexibility. So towards the bottom, you've got these general purpose single board computers like the Raspberry Pi that can kind of do anything. And while the products at the top are pretty easy to use, as you go down, what typically happens is things take they're a little bit more complicated. So if any of you have used Raspberry Pi, for example, from scratch, got one out of the box and set it up, you might have found it was a bit involved just to get going. And as I mentioned before, with Gadgeteer, we wanted to get the best of both worlds. We wanted this very low threshold to get going, but quite a high ceiling. And I think our school pilots showed we actually did a pretty good job. I've got a couple of quotes here on the slide, and both of them allude to the open-ended nature of .NET Gadgeteer. So one student said, well, you can be creative and make anything, really. You weren't limited in what you could do. You could take an idea anyway. And another student commented on the fact that once they built something, they could iterate on it. They could always add more functionality. In part, this was enabled because we actually had over 100 different hardware modules that you could use with a Gadgeteer system from 8 different manufacturers. But there was a drawback from all this. And I've got a couple of other quotes here which illustrate this. So one of our teachers in one pilot commented that they had to deal with a problem because the version of software they had wasn't quite compatible with the set of modules they had, and it wasn't quite clear. It caused them some confusion. And another comment that I picked up from online is quite correct, was that the way that we designed Gadgeteer, not all of the processor boards were compatible with all of the module boards. And that caused some confusion as well, as you can imagine. Now, I mean, we documented it, of course, but if you're a busy teacher, you might not have had time to read all the documentation. So when the opportunity to work with the BBC on the microbit came along, we were super excited. We wanted to go further in terms of that low threshold. We wanted to do something that gave immediate results, something that always works in the classroom, where you didn't have to worry about what software to install, where students could never get distracted because they were waiting for some software installation to finish. So we created a web-based experience that needs no software installation. You just run it in the web browser. And from a hardware perspective, we made this very simple, small device. It's got a display built into it, basic sensing built into it, so you don't have to attach anything to get going. Now, of course, we didn't want to compromise on that high ceiling either, but with microbit, we took a slightly different approach. We've got this edge connector on the side of the device, and it's possible, using the edge connector, it's possible to extend the hardware. You can use crocodile clips to connect these little holes here, and doing that, you can connect simple bits of hardware like headphones or an extra button or an LED. But there's also an ecosystem of accessories you can buy that the whole device plugs into. So you can buy little robots and you plug your microbit into the robot, and then the microbit controls the robot. And from a software perspective, we have this notion of packages that can be added in the web browser, so that depending on what hardware you want to use, you can make sure that the programming environment supports it. Another aim for microbit, of course, was low cost. And the component cost is actually less than $10, which means these devices retail for about $15. And we've now made 5 million microbits, which we estimate to have been used in a meaningful way to learn computer science concepts by 25 million children. So in a sense, we've achieved our goal, right? Physical computing is much more accessible than it was before. 1% of the children on the planet have used this device. But of course, we all know that accessibility is multifaceted. And one issue with microbit perhaps is that the composability that we had with .NET Gadgeteer is limited. So we've been working on a new system in MSR, which we call JACDAC. In many ways, JACDAC is a standard for physical computing. It's a bit like USB, but for low-cost microcontrollers. So somewhat like .NET Gadgeteer, JACDAC is a modular system. So you build a new hardware device by plugging together different modules. Everything uses the same type of cable, and the cables provide power as well as connectivity. Unlike most existing physical computing systems, each device presents a common interface electronically, so interoperability is built in. It doesn't matter what kind of accelerometer you have or where you plug it in. It's much like plugging a USB webcam into your PC. It should just work. And we've managed to do this, hopefully without increasing cost, a key factor, as I mentioned before, in keeping the technology accessible. So JACDAC is still a work in progress. We have some early prototypes, and we're hoping to have more prototypes in the first half of next year. And one of the things we'd really like to do is get your thoughts and your feedback on this system, on what you might find it useful for, and also perhaps new modules that we might be able to build specifically to address particular accessibility needs. So I put my first thoughts, as it were, on the slide here. These are probably very obvious examples, but if you were working with microbit, perhaps you could plug in a larger display or larger buttons, perhaps a different type of feedback, haptic feedback. for example, or just different modalities. But more than these simple examples, perhaps we can unlock different experiences for physical computing, like the physical programming experience that Cecily and others worked on with the other Microsoft research project, Code Jumper. So I hope that's given you an idea of our aspirations to make physical computing more accessible. And the final part of my talk, I wanted to come up another level, in a sense, and think about accessibility much more generally. So let me return for a moment to the definition of physical computing. We've got combining software and hardware to build an interactive physical system that senses and responds to the real world. Now, if you think about it, every time we use digital technology, we rely on some kind of physical computing to bridge between our physical world and the virtual world of the computer. The keyboard and the mouse and the LCD monitor that I'm using right now are examples of this. And of course, they're the standard forms of interaction for most of us. But by using physical computing, we can build alternatives to these. We could debate different types of tangible interfaces. We can think about sensors that maybe automatically detect the context of a user. So maybe I've got a sensor on my door to my office, so that when someone opens the door to my office, I automatically go on mute in case I'm just about to be interrupted. And we could also think about experiences which are targeted at very specific user groups. So these could be completely new devices, not just things like new versions, as it were, of the mouse and the keyboard. These could be completely new, maybe standalone devices, and not related to interaction with a regular computer. So I wanted to give you one example of this. This is a smart walking stick, and this idea actually came from one of the schools who took part in our Gadgeteer pilots that I mentioned before. We actually ran a competition amongst these schools and asked them to come up with ideas of what they'd like to build with Gadgeteer. And so this was actually one of the winning entries. These students said, well, they wanted to make a smart walking cane. So it was going to have a camera on it and a little push button, so that if you were using the cane, you don't have to worry about fiddling with the camera. You could take photos as you're out and about. You could easily take photos. But more than that, it's also got motion sensors in it. So it's got an accelerometer and a gyro, and it would automatically detect unusual motion. So if the user dropped the stick or fell over, perhaps, and the stick fell, it could detect that, and could use that to take a photo as well. It also has a cellular radio, so it could send messages in the event of one of these incidents, and it has GPS. So if it needed to, it could alert someone as to the location where this incident had happened. So our vision for physical computing goes beyond creating the engagement with technology and creating an engagement around computer science education. We see physical computing not just as a tool for education, but a tool for makers and ultimately for everyone. A vehicle for people to think creatively about technology and to build their own interactive devices. We think it's super important because it means in a world where increasingly we're all becoming technology consumers, actually we can redress that balance, and we all have the potential of becoming technology creators. We think physical computing can empower organizations and communities and individuals to build solutions to address specific needs. It's not just doing it in order to learn and to understand. It's an end in itself for many people. And we think this ultimately is what's going to empower everyone to get the very best from what technology has to offer. Thank you.
Thank you, Steve. Super interesting stuff. It's really great to see how the UK has really embraced the sort of educational arc of computer science education for K through 12 and beyond. And and it's super interesting to see how something like Gadgeteer and JACDAC could plug into that, unintended, not intended. We do have a few questions and we have 5 minutes. So I'm going to encourage you to answer each of these questions fairly quickly, about a minute or so for each one. The first one is, you've talked about empowering people to build prototype devices to suit their particular needs. Do you have any thoughts about scaling up? How would you go about making more copies or making a product for others to use? Okay,
super interesting. So I'll try and do this. This is a really interesting question. I thought it might come up because it came up yesterday in our discussions in my workshop. I'll try and be brief. So we think of prototyping, right? And it's interesting to drill down on what that means. Because a prototype is really just the start. Some people sometimes think, well, now I've got a prototype, I could just make copies of it, right? Like photocopying. And you know, with documents, we can make copies easily. With software, we can make copies easily. But with hardware, it's actually really hard. So a prototype, if you think about it, you might have one of them, or maybe you have a few. And if you've got it right, it will kind of work like you imagine, and it looks like roughly like how you imagine. But sometimes that next step of going to a product, that might actually be overkill. You know, because a product you might be making tens or hundreds of thousands of a year, it, you know, might be super cost optimized. There's a lot of complexity in doing that. And making this transition from prototype is actually remarkably treacherous. You know, I put some publications here which talk about why this is, but you know, I'm sure we've all heard of Kickstarters that failed, where there was a prototype that had all the promise, but turning it to product turned out to be really hard. And so we have a separate, maybe we should, you know, if people are particularly interested, we could take this offline, but we are developing tools and techniques to cross this treacherous chasm, as it were. But we also think it's useful to introduce a new term, which we call isotype. So if you think about it, a prototype technically means the first one of, that's what proto means, only one of it really exists. The moment you have multiple copies of it, they're not all prototypes anymore. And so we think of them as isotypes, they're equivalent copies, but they might not be fully fledged products yet. And we think this process of isotyping is actually ripe for the research community because it requires, first of all, it gives you a new perspective, I think, and it requires new tools. And ultimately, we think that we can create a solution that helps people do this scaling, which might fulfill the needs of a particular community or individual because they only need 10 or 100 particular pieces. Or it might also just act as the springboard to test out an idea better. It might help researchers really evaluate an idea at a bit more scale before they then make that next step. Okay, sorry, I must stop there.
Great. I think we have time for just one more question. For everyone listening and asking questions, your questions will be shared with the speakers. So if they're not able to answer them live during the talks, they will be encouraged to answer them offline. This last question, I'm just going to read sort of the second half of it, where I think the meatiest part of the question is. It's from someone who works at a micro school for students with learning disabilities. And the question is, are there training supports around physical computing that could help us learn while we are doing, and or any people, organizations out there that are interested in partnering with a micro school that functions as a learning lab? Do you come across anything like that?
So the broad answer is absolutely yes. I'm not familiar with micro schools, and so I don't know which of the many, I guess, support mechanisms that are out there would be most suitable for you. Perhaps the easiest thing for me to do is try and find that question in the chat or whatever, and post some links. But there's a big variety of physical computing solutions out there. I put some of them on that slide. But for most of them, you'll find lots of resources online. And so these are things like teaching materials. So certainly Microbit, which is one that's close to our hearts in Microsoft, and the MakeCode programming environment that goes with it. There's a huge amount of resources and tutorials and guides, as well as stuff you can buy to go with it. Troubleshooting guides. Arduino is very similar. There's a lot of stuff on Raspberry Pi.
Great. Thank you very much, Steve. Very much appreciate the talk, the rapid fire responses that you gave us for these questions. It's very exciting stuff. And we look forward to seeing what happens to JACDAC and Gadgeteer in the future.
Thank you.
Thanks.